Muppalla. I'm currently a student in UC Berkeley's MET program, pursuing a dual degree in Eeks and Business, and I've been trying to get more involved in terms of computer vision related work. So yeah. So today for support vectors paper reading, I'll be going over NeurIPS's 2025 conference's best paper, Why Diffusion Models Don't Memorize, the role of implicit dynamical regularization in training. So this paper tackles like a very critical question as generative models keep improving. So traditionally, deep learning theory suggests that when a model is like highly over-parameterized, first what that means is, right, so when a model is highly over-parameterized, it has a certain number of parameters p that is far more greater than the number of training samples n. So if that's the case, if there are more parameters than the number of training samples provided, then it should realistically eventually be able to fit in all these training samples immediately and essentially perfectly memorize the training points. So it should eventually reach a zero training loss at the end. Now, that way, if a model is able to learn all of these specific training samples that were given, it should be bound to reproduce these samples at the end of the generation process. But that's not the case for diffusion models, even though they are known for being highly over-parameterized, right? So that's what the question is being raised in this paper. It's asking, okay, well, why don't diffusion models memorize, right? As explained here in the title, I'm just going to underline this here. So why don't diffusion models memorize despite being highly over-parameterized? Actually, it even ends up producing really high quality novel data, despite all this amount of training data that's given. So before I go into the author's findings, I want to first give a quick overview of what exactly diffusion models are and a surface level understanding of how they work. So in this current era of AI and generative AI, diffusion models are basically the state-of-the-art tool used for generation in many forms. It's generally known for images, but it has transitioned into generating audios, scientific data, videos, even text as well. But the main gist is especially in images. Now, a simple way to understand how diffusion models train is it can be considered like a two-stage process. Right, so here the first one is the forward process. So in the forward process, it's used to essentially create this new sort of training data. You're given these clean images of this training data as input for the model to learn, but with this initial like training data n, it creates this new training data that I'll go over like n star, right? So what does it do to go from n to n star? That's where the forward process is, right? So it takes these clean images that are given in n, and it gradually adds Gaussian noise, right? So at each time step, right, t1, t2, so forth, t of n, there's some amount of Gaussian noise that gets added to the initial clean image until it reaches a pure static state. So let's say I have this like image here, right? Let's just say it's just a white image, white like colored image. And then at each time step, you add some sort of like noise, right? Like this. So that could be time step T1, and then time step T2, more noise, and then so on and so forth until basically all of these pixels are just noise. And you can also call this final noise image as like another way is pure Gaussian white noise. So that's basically what forward processing does, right? It takes these clean images and adds a bunch of these noises to get like a Gaussian noise distribution at the end. Now here in this forward process, the model itself, it doesn't do anything during the forward process. This process just provides this additional training data that will be used in the next step, right? And also during this additional noise in each time step, it's a way to label how much noise was added in that specific time step. So how this is done is it also, let me write this, adds label of amount of noise and specific t, right? I'm just going to say t of I. And this is done through a mathematical, I'm just going to write it down, stochastic differential equation. So that's what's used to label the noise added at that specific image, at that specific time step. A quick example is just like, for example, if you have like, a training set of dog images, right? You want to teach the model what a dog is not, right? By destroying this image. And what that means is you keep adding noise to it. So at the start, you start with a clear, high resolution image of a dog, right? So just say this is, the dog image. And then you gradually add noise, as shown here, to the dog image in these tiny steps. So after all these steps, the image of the dog is completely gone. It's just a bunch of random static noise. That's all you see. Random pixels of white noise. So during this process, it just reiterating, it records exactly how it corrupted the dog at every stage. So it creates the labels the model needs to learn. Okay, now that we have an understanding for forward process, the next part is backwards process. So that's where the magic happens, and it's used for both training and inference. So during the training, let me go to backward. So this is the forward. All right, I'm gonna go down here. So this is the backward process, right? So during training, whatever noise that was generated from the forward process will be used in this backward process. So here it's shown all these noisy images that were created in the forward process, and it's tasked with predicting the noise at each time step. So the model generates new data through this, assumingly, right, by reversing what the forward process does. It reverses the stochastic differential equation. So this reversal, though, to determine how much to remove at each time step, you need to learn the score function. So the score function is like a vector field, right? It's like the velocity of where each pixel or each value in this image should go to eventually get to the clean final output. So yeah, in practice, we learn the score by minimizing the score matching loss. And to do this, there's a specific architecture within diffusion models called the UNet that learns the score at each time step. Right, so if we just quickly go back to like the dog example, right, we're given a block of pure random noise, so no specific dog image is visible. Then based on what is learned from the noise that was generated in the forward process, it tries to figure out what parts of the dog are hidden within this static noisy image, and which way to move all these pixels to reveal specific, like a general idea of what a dog is. right? So in the final output, you'll get a clear image of a dog. So yeah, I just wanted to give a sort of an overview of what a diffusion model is before we go into the author's findings about, okay, so backwards process, you're removing it to get a clear output, but how is it able to output new images instead of just specifically from the training sample? That's what the authors are essentially trying to figure out. I think just two things I want to mention, two words, are the empirical score. So what empirical score is, it's basically, right, when you learn the score function, if you end up learning the empirical score, that's just learning the training sample. And we don't want that, right? Because if we do that, then at the end of the backwards process, the model will just output anything that's from the training data. It's just going to be copy paste. So that will be like a bad mapping. Right. By mapping, I mean like, because each time step you're mapping from the current noise of or the current way the image looks at that time step, and you're mapping it to the next time step and so on. So how does the image look at each time step, and does it get closer to a realistic output? And then we have our population score. And this is what we want to aim for, right? We want to aim for example, we want to get a good distribution of basically all possible like dogs in this world. We want to make sure that no matter what sort of input that's given, it can realistically output something new than whatever training data was given. So this could be like a good mapping. So I'm going to represent like the distribution of all possible data, right? I'll be basically using these two words like throughout my reading, and also to explain a few diagrams as well. So yeah, I want to first go to this diagram right here on the right, because there are generally two variables that really determine how our diffusion model will perform. We have our value n, which is the size of your training set, right? And then you also have p, which is the expressivity or the number of parameters in your model. So how big the model's brain is, right? So that's already listed here on the two sides as well, two axes. And another thing that's shown in this figure is n star p. So what that is, it's like the model's threshold of how much it can really understand, even if the amount of data is much larger than this threshold, then the model can never truly get the full evaluation or the full like empirical score ever, even given that much data. So here you can see that this figure here is divided into three regions. So the first in the bottom is the memorization field. As you can see that n, the size of the training data, is much smaller than the model's capacity, right? And is much less than p. So that means that it's highly over-parameterized. So eventually, not only will the model like remember everything, but it will just be really easy to just remember everything within this data. So there's no chance that it can even like find any sort of generalization. It will automatically understand this training data. Then we have at the top the architectural regularization. So this happens, right, when the size of the data exceeds this threshold. right? So here, the model won't ever be complex enough to memorize all features of the given training data. So what the issue here is, though, is that sure, it can output very unique data, right? So it can output novel data, but it's not going to be very high quality data. It's going to be very blurry or not very generalistic, so nothing in detail. So we have this third region here, which is dynamical regularization. And this is the most exciting part within this paper, because this is where a lot of the author's findings are. And the core thing is that, yes, the number of features of the training data is much less than the model's capacity or the threshold. So it should eventually be able to memorize all aspects of the training data. So the question here is, how is it still able to generalize and even output high quality and novel data? So within this dynamical regularization section, the authors find two timescales that emerge. So the first one is they find T of gen. And this is the generalization time. And you also have T mem. And this is the memorization time, when eventually the model will understand everything within the training data and just start copying. So there's two timescales, right? One is when it starts to generalize and kind of get an understanding of what this distribution is and outputting kind of novel data. And then there's T of mem, where it just copies from the training data. So this is kind of the idea or the figure to explain this overall findings of the timescales, right? So if you have here, you have the T gen and you have T mem. So that means there is some sort of interval within here that indicates that this diffusion model can output very high quality images. But once it reaches T mem, this memorization regime just increases, right? It goes to just copy pasting. That's what the memorization fraction indicates. It indicates how much of these outputs are from the training sample. And you have your inverse quality here. This is just another metric to show how high quality it is, right? So the lower it is, the much better and realistic it is. So this is like the safety window for what makes diffusion models not memorize. So that's one of the findings. The key finding here, though, is as you add more data, right? So as this value, n, as it increases, the time of when the model starts to memorize also increases. So it gets pushed further and further back. It is basically growing linearly with the size of n. So although the time for memorization basically shifts, the time for generalization just stays the same. Right, so T-gen is the same. So this is a very crucial breakthrough finding because it actually creates a massive window where you can just stop training and get original high quality results. So I've been saying this for quite a while, but the word for this is known as, go down here. I'm gonna write here. So the word for this can be early stopping, right? So early stopping is you want to halt the training during this window. So that's usually when you want your training to stop in diffusion models. So between T-gen and T-mem. So just a review, basically what the authors explain is that as you add more data to a model, right, so as n increases, the time it takes to start memorizing also increases as well. So this is the widening gap because it causes the time of memorization to keep getting pushed back. And it creates a greater window for the time steps and to determine when you want to stop the model. So, okay, well, why does it take so long to memorize? Let me just make sure. Okay. Also, feel free to ask any questions as well. I know if in case if anything it might sound like a repetition, I don't mind saying it again as well. Okay, so moving on, right? We know that as the size of the training data increases, the time of memorization also gets increased and pushed back. So why does it take so long to memorize though, right? Why is there even a time interval between generalization and memorization right here? Why aren't they both just the same time? Let me go down. So the key here is, as mentioned here, there's something called irregularity of empirical score at low noise level and large N. So what this means is, like, if you think of it in the big picture of what some object that's easy to follow, right? You kind of have a gist of what like the features of a dog look like or the face of it. But the specific unique details of it, of a specific breed, are very hard to notice early on, which is why the model takes longer to notice these complex features and detailed findings as well. So it goes from the smooth path first, right? And then to the more detailed, fine-grained ideas as well. So this term can also be considered spectral bias. So this is a very quite a fundamental concept where neural networks are biased towards learning these low frequency of simple smooth patterns before they learn these high frequency complex patterns. So usually it learns, right, low frequency first, and then you go to learn the high frequency. So that's the sort of the general idea in like the theory that these authors found to explain this difference between time of generalization and the time for memorization. Now, to go from theory to practice, they provide both numerical and analytical sort of proofs. Right, so I'm gonna zoom in here. So they first actually, I'm just gonna give a gist about this. They first, for the numerical experiments, they use the UNet and train that using images of the celeb A dataset. And then on the analytical side, they focus on class of scores constructed from random features, neural network, and have some results following that I'll further explain. Oh, second. All right. This is a bit of like the math side of just understanding how the diffusion model works from forward process and the backward process. So I guess, yeah, I can go over a bit about how the math of it works overall. Just a quick idea, as explained before, for forward and backward process. So for forward process, it introduces stochastic differential equation, SDE, right? It's an equation used to model and label this random noise over time, right? So that's used for the forward process. And then for the reverse or backwards process, we use the reverse of, we use the time reversing of the standard, the stochastic differential equation. So like if a noise is a fog, the score function, right, that is used to learn how much to decrease the noise tells exactly which direction to lead back to the clear and real image. So another thing is like you can also use ordinary differential equations, but that's more for a flow matching that can be used in the future as well. Let me see what else. So there's one catch though, which is, right, eventually there's this thing where the authors will find out about the empirical score. So I wanted to actually go back up here, right? So in this image here, you're given the interval of the generalization window and the memorization after and before that. So this gray distribution here represents the empirical score, not distribution, but this gray diagram here represents empirical score. The black dashed lines represent the population score, and the orange represents like the model's understanding. Right. So if you notice here, it's sort of like a line here, and then in this, between these two between this interval, it has this sort of understanding of what the population score should look like. But once it reaches TFMEM, it eventually goes to the empirical score. Right, so when it does eventually, right, when it does reach that state of the empirical score, that's when the map is like too perfect, but also not what we want. So it should memorize everything because that's the easiest way to lower the overall score matching loss, right, to 0. But it doesn't do that, right? Because as stated in the region of implicit dynamical regularization, it forces the model to find the smooth patterns or the smooth estimate of the score first. So it learns these general rules of what a certain object looks like before it starts thinking about the specific pixels of, you know, as in terms of the celeb A data set, like this, a single celebrity. So the next section here, it will go over the numerical analysis or the numerical sort of proof and experiments on the celeb A dataset using the UNet architecture. So here in section 2, the authors kind of focus more on training a unit on a dataset of celebrity faces, which is called celeb A. And there's two things they tracked, right? How good the images looked, which is the quality, and this measured by the FID metric, and whether the model was just copying off from the training samples. So that's the FMEM metric. So FID metric basically determines how realistic plus how much quality. Is it high quality? So the lower the FID, the higher the quality and the more realistic this image is. So let me scroll down here. So it's shown here. These are the two. And it's, so if we see here, this is basically the output of the diagrams that were trained using the celeb A dataset on the unit. So on the left, we can see that as the time steps keep going on, the value of the FID actually keeps decreasing. So that indicates that it's getting more realistic and of better quality. But then once you reach here, these dashed lines represent the increase in the number of samples that are from the training data. And the same thing can be said for this image right here, right? So as the loss, there's a difference between the testing loss and the training loss. Right. If you see here, the training loss and the testing loss are basically the same until you reach this point. So that basically indicates that the memorization time is around here, and as the T of mem keeps, so this is T of mem, as the time steps keep going on, you'll notice that since the samples are now just from the training data, the test loss will actually keep increasing, right? Because it's not getting it's not getting the returns it wants, and the training loss will decrease, right? Because it's basically just getting the exact stuff from the training sample. So this is like a good indication of how the T of mem is kind of determined, and also where T of gen is kind of getting an idea, right? So for T of gen, it should usually be when the FID is as low as possible and stays constant. And here, the T of mem can be seen as when the loss kind of distances itself from each other between the training and the testing. So the main things that are found by the researchers here is that there's, for generalization, within the first 100,000 steps, the quality becomes much better, but the memorization fraction, right, it still remains 0, indicating that it's still within the generalization window. Then you have phase 2, which is memorization. So this is much later at a time, right, T of mem. So this quality doesn't change, but the model starts outputting exact copies of these training photos, and it becomes like a copy paster. And the most important discovery, right, in here in this numerical proof is kind of how these times change when you add more data. So, right, so they found that while the phase of Tgen always starts at the same time, the T of mem is delayed linearly by the amount of data n. So if you double your training images, you double the time you have before the model starts memorizing. So this kind of creates a window of safety where you can stop training and get much better original results. Trying to find, yeah, as stated here, right? If you could, T of gen is around 100,000. But the test loss still remains close to the training loss even after 11 million time steps. So that indicates that T of mem is much farther away than, and much wider than needed, much wider than we expected. Yeah. So the next important thing that the authors kind of look into is the width of the UNet architecture, right? How many parameters can this model withhold? So the width of the UNet actually has a huge effect on the parameters, right? So here is stated the effect of the model capacity. They want to study more precisely of the model capacity on this transition. So they try to vary the number of parameters p by changing the UNet base width. So they vary this, right? They model it from 16 to 64. So what that does is as the width increases, p increases. So why do they even want to test this in the first place? It's because in the end of the day, we want to see if we can use these models real time. So does that mean a bigger model can help memorize faster or generalize faster, or can a smaller model actually end up doing this much better? So that's kind of why why the authors kind of try to vary the values of the width as well. So if you go from like 16 to 64 for the width, the number of parameters can jump from like 1 million to 16 million. So I'm going to write this width. So the more width, right, it equals more parameters and more expressivity, enough to fit in more training samples and more complex data. So there's one great relationship that was a few key relationships that were found through this testing. The first one is, right, for the generalization time, T of gen, here, a bigger model will actually reach higher quality and novel images much faster. But then also that can be said the same for T of mem. So a bigger model also starts memorizing a lot faster. So both of these relationships are inversely proportional to the width W. So if you quadruple the size of your model, of the width, you will effectively cut the window between T of gen and T of mem, the time for generalization, and time for memorization by 4. So if width, right, if you multiply this by 4, then T gen, T mem, this size will be a fraction of it as it was before. The only way that you can increase this interval is by increasing the size of the data, right? Because that way the tmem will basically grow linearly as size of the data set increases. So if we go back up here, right? If we look at the phase diagram on the right here, it plots the size of n with the parameters p. So if your dataset is too small for the model size, you'll fall into this pinkish area, right, of memorization immediately, right? You'll fall into this zone immediately. But if you do have enough data, you'll stay in this generalization zone. So the line kind of moves as training continues. So that shows that eventually almost any model could memorize, but this implicit regularization keeps it safe for a very long time from reaching that time of memorization. And this is furthermore just like some similar diagrams that were shown from previously, where you can see the fraction of training samples that were outputted, and this was the FID, which determines how high of quality an image is and if it's realistic as well. Yeah, so you can see also like the relationship between these as well. Yeah. So yeah, this was one of the two kind of analyses or tools to demonstrate their theory. The first, right, we just showed was we looked at units and these celebrity faces here and determining how the generated output looks like. Right, so here this was demonstrating how units can help improve the time of generalization and time of memorization. Now, the issue though when it comes to units is that they can kind of be like black boxes, right? They're a bit too complex when you want to get the mathematical understanding or more of a pen and paper kind of explanation. So there's another network that the authors introduce, which is called Random Features Neural Network. So essentially this is like a two-layer network, right? The first layer is just a bunch of random weights that were generated through like Gaussian distribution, and they just remain frozen. Then you have the second layer of weights, which you can see through matrix A, and this is learned during training. So why is this used in this case? It's kind of a simple way to use and calculate how a, a diffusion model learns. It's powerful enough to show the same generalization, memorization behavior that we see in diffusion models. So yeah, essentially the point of this is to understand the training dynamics associated with decreasing this empirical score matching loss at these fixed diffusion times of t. So here the authors look at a few of these equations down here. Here the authors look at gradient flow. So this is the mathematical version of like going downhill and minimizing the error in denoising. So they found that the speed of learning is determined also by the eigenvalues of a specific matrix U. So U is essentially the correlation matrix here, right, of these random features. So yeah, it determines how fast the model can learn different parts of this data. So that's what the correlation matrix is used for this explanation. And the authors also look at gradient flow, right, as explained before. So to understand if whether or not this sort of random features neural network really works, like diffusion models do, they just introduce two equations, right? Epsilon score and here. All right. So this measures the distance between the model's map and the true map of this data. So if this number is low, the model has generalized. Now, if the generalization loss is high, then it means the model is just memorizing the training noise, which we don't want that to do. So here, this is the generalization noise, and this is the difference between the testing and training. And this will, yeah, measures the quality of the generation, or quality. So here, this is just like a setup for the random features neural network, the speed limit matrix, right? The correlation matrix U, and some of the quality metrics as well, right? As determined for loss and the score. So here now we want to, here the authors kind of show the spectral gap. So this is actually the big picture, right? Of understanding actually how this time of generalization is much earlier or before than the time of memorization. So here is just like an illustration of a random features neural network. You have your random weights that were generated as W, and then you have your matrix A that it trains on. So here in this page, we look at the spectrum of U in here and here. Right, and it's based on the distribution of eigenvalues, right? Or like the probability distribution of these eigenvalues to determine how fast these models learn. So if you look at the histogram here, there's basically, right, you can't really see it, but this is basically one bulk, and this is the second bulk here. So the eigenvalues are not all like bunched together. They form like two different islands or bulks. That's a huge indication of why there's generalization before memorization. Here, if the larger the eigenvalue, the faster it is to learn these patterns of that specific value that correlates with this eigenvalue, right? So this is much faster to learn. So a higher eigenvalue basically indicates generalization. And then later on, when you have much smaller ones, this is the memorization. Right, so just repeating again, the second bulk, right, this orange bulk right here, these are the large eigenvalues, and they represent this big picture of the general shapes and features of a certain population based on the training data. Now, because these numbers are large, the model learns them almost instantly, right? This is why it's called the generalization phase. Then you have the first bulk. Now, these are the tiny eigenvalues, right? Values almost 0.2, 0.4, basically near zero. And they represent the noise or specific details of individual training images. The stuff that makes each output unique from one another. So because these numbers are much smaller, the model takes a longer time to really learn them, right? That's why it's called the memorization phase. So hopefully that was understanding of how the RFNN kind of helps understand why in the unit and in diffusion models, it's not able to have the memorization and the generalization time the same. So if we go down here, right, this is the evolution of the training and test losses for RFNN. So the score here, right, the quality metric, basically against training time here. And you can see that this loss kind of once again gets an increase in difference between the testing and training. And okay, perfect. So I guess the last thing in this case is, right, here it lists several variables, right? You have all these variables here that define these type of bulks, right? These calculate the relationship between the noise level, the variance, the model's activation function, and so on. So the key takeaway though here is the spectral gap, right? Let me just go back up, right? This distance, do different. The spectral gap, right? The empty space between the two islands is what creates the window, right? For when a diffusion model should stop training. So the wider this gap, the more time you have to stop training before the copying mode gets in. So theorem, I'm going to go down to these two main theorems to explain this better. So here, theorem 3.1, it provides the equations, especially for the random features neural network, and it proves that the position at the first bulk moves closer to zero as you add more data in. This is, okay. I'm just gonna write the generalization of how this works, right? So, oops. Bulk 1 moves closer to 0 as n increases or even, approaches to infinity. So this is a clear proof, right? As you add more data, it makes the tiny eigenvalues even tinier, which is what makes the memorization time increase linearly with the size of the training data. So essentially, right, the model will be run at two different speeds. It races to learn the general population score using the large eigenvalues, and then it goes and learns much later on the empirical score using the tiny eigenvalues. So that's the basic idea of implicit dynamical regularization. Then I'm just going to quickly go over theorem 2, right? Here, it's where your parameters is massive and there's a huge amount of data. So there's two distinct like regions, right, of the diffusion model. As explained before, it's over-parameterized where p is much greater than n, and then when it's under-parameterized where n is much greater than p. So here, right, this is the focus of many diffusion models. It describes models like stable diffusion, where the model has more space in its parameters than there are unique images in the training set. Then we have here under-parameterized as well. And one more sec. Okay. You have st squared. So this is kind of the parts of the model that don't really contribute to learning or memorizing. So this part doesn't really change the loss as well. So overall, this is kind of the main idea of how this informal density works, which is explained here. This is basically, get a better idea. So yeah, as well. Okay. Okay, so I'm just gonna go. Okay, so yeah, for theorem 3.2, it breaks down the models into three parts, right? You have like the irrelevant peak, which I'm gonna go back up here. Right, you have the irrelevant peak, right? That doesn't, which is kind of like the dead weight that doesn't really matter or affect the distribution. Then you have the first bulk, right? These are just the small eigenvalues, and then these are like the general as well. Okay. Yeah, so this is just like a sort of a mathematical demonstration of the idea of generalization and of memorization, right? So this window, okay, so this window, right, if you have tgen to tmm, it's not like just some sort of observation. It helps you understand why these two values of generalization and memorization have completely different frequencies and can capture one without the other simply by just stopping the time step. And yeah, this is basically the overall explanation for this paper, right? So the main thing about this paper is that the reason diffusion models don't just copy paste their training data isn't just by some sort of luck. It's based on all these features that are seen throughout the training and the sort of interval between the artistic creative side and then the memorization side, right? That's where implicit dynamical regularization comes in. It's very dependent on the size of the training data as well as how large the model is in relation to it. So these models are just more biased towards generalization long before they, go more into detail, which is where memorization from the training sample comes in. So as we've seen, the safety window just keeps getting wider as you add more data, and that means essentially the most powerful models are often the most creative. So a very cool takeaway, right, is I wanted to highlight this especially because even though this paper does focus on diffusion models, anything that's related to score learning mechanics, right? For example, flow matching and stochastic interpolants, all this generalization window will also likely exist in almost all of this modern generative AI models. So whether the model's using some score function or like a velocity field to move these noise away as like a mapping, it kind of ignores noise to find structure, and that's what makes it remain the same for all these types of generative models overall. There are few things to just keep in mind, right? Right, kind of mentioned that most real world models use Atom as an optimizer, but it's a lot more faster. Instead of right the standard, standard gradient descent used, stochastic gradient descent used here overall. So it still does work actually, especially for the Atom optimizer, but it's just much faster. So early stopping kind of becomes more critical here too. So there's a lot of new things that were found throughout this paper, and it kind of helps a lot when it comes to future creations of models and making them more efficient to run in real time and figuring out where to make it more useful in training, how to decrease the time of training, maybe even decrease the amount of hardware used for all this as well. So a few things obviously is one, you want to control this capacity. Don't make the model's parameter size unnecessarily large if you have especially very little data, right? If that's the case, then it will honestly just decrease the interval between T of generalization and T of mem. So make sure to control the capacity of whatever models are being made. Then it's also trying to figure out, determine the gap of when the training loss and test loss occur. And finally, I'd say like another thing is to consider is the FID metric, because once you have a final stabilization of high quality and realistic results, that's kind of when the T of gen appears, and that's when it occurs, right? That's when T of gen, the value of T of gen is, and you can do early stopping around that time as well. So anything that's gained after that point is probably just like memorization after that window, right? And that can even lead to privacy leaks if you input your own data and the model outputs something similar, and any sort of issues in the future as well. So yeah, it's a great paper that shows how to understand like the spectral bias, the gap between these eigenvalues, and how we can build models that just don't repeat like the past. Because a lot of the industrial models also seem to actually have taken notice of outputting a lot of data that is just from like the training samples as well. So I guess diffusion models, this finding in diffusion models is very key to create like a new image or face instead of just some sort of forgery that occurs later on. Yeah, so hopefully this was this I just hopefully this paper reading was understandable, and thank you so much for attending this paper reading on why diffusion models don't memorize.
Sneha, it's more a statement that they memorize much, much later. You never reach that. You shouldn't reach that. It's best to stop earlier when they have learned generalization.
It's sort of trying to understand. It should be able to memorize, right? It should eventually memorize,
Eventually do that. Yes.
but why does it not do that?
Yeah.
Because there's this interval.
Yes.
That's when the model stops training.
If I am right, there are earlier papers that show that if you go on training these models, they do actually get worse after some time. And I think the value of this paper is that it shows why.
Mhm. As in, like, it just outputs, like, the training samples and stuff like that.
No, so there have been, I can't specifically remember the papers, but there have been some papers recently that showed that if you go on training diffusion models for a very, very long time, you actually don't get better models, you get worse models. So,
Oh, mhm.
so of course, that's memorization, that's overfitting. It does eventually kick in, but or that's how I remember. I may be wrong, but that's how I remember. When I look at this paper, what it's essentially showing is that the spectral analysis shows that, see, generalizations are the, like you said, big eigenvalues, the big eigenvector modes.
Mhm.
They can, or they get learned much faster on a much earlier time scale than the memorization time scale. And the bigger the data set you bring, the quicker it's able to pick up the generalizations. And
Mhm.
and the gap between the time to generalization and the time to memorization keeps widening. So you have a pretty big metastable basin in which you can use the models before it starts showing degradation.
Yeah, I think that's basically the really cool, like, key finding here.
That's
So
right.
it's kind of like you can basically add more data, which should make the model produce better results. So that's kind of, yeah, that's the interesting part of this overall. I think it still hasn't been tested on, I think, on flow matching yet, but it's since it's also a sense of score matching, it should be able to work for that as well. Yeah, if does anybody have any other questions? I can also scroll down to.
Yeah, I had a question. You mentioned the use of Atom Optimizer. I was curious how some of the newer optimizer research, like Muon, performs on diffusion models. If that is even applicable to these models, or
I guess I'm not too sure about the other optimizers. I think it's more of the understanding how if useful would be, or like if this would still remain the same if you use an atom optimizer. I'm not too sure. Like, are there other optimizers that like you were
No,
thinking of?
they mention it in the future work section that
Okay.
they have done this work with stochastic gradient descent, but
Yeah.
the work to see if this finding replicates with even Adam is yet to be done. So that's the first bullet point they mention.
See, that's I guess yeah, that's some future work to look into. They do actually, yeah, they do trust on. Let me make sure while we derive our results. Yeah, so there's some like further sections here that they do go over the atom optimizer as well. So it does also work in this case. But the only two that were tested on were, yeah, atom and the SGD. So yeah, that's definitely some, I think, the future work that they mentioned to test out on other types of optimizers as well. Let me go here. Yeah. So could possibly honest like for atom optimizer, it actually even decreases. It makes the time of generalization much faster. So if there's another optimization that's similar to atom or performs faster than SGD, then it should also have like a relationship in that way with the time interval and when it starts.
Okay.
Yeah, I suppose, Richard, to your point, see, the muon optimizer works typically on 2D parameter space, like and filters and convolution filters and so forth. So those are there obviously in the diffusion model. So I suppose that question is worth exploring. How would that perform, at least for the applicable components of diffusion?
Yeah, I did some experiments over what 2-3 weeks back on Adam versus muon for small GPT-based models. It was a bit inconclusive. It seems that there's a data dependence aspect that what I found was muon was, I think, faster, but it was less. The loss was, it was not converging at least as fast as the Adam was. But many other people have reported the reverse of that. So I was interested to explore in diffusion models. Is the picture different, or is it more stark?
Yeah, Richard, actually, muon, I haven't kept up with the muon research and as it has evolved, but my early recollection from the first paper was that they specifically say it's limited to 2D parameters and things like filters and things like that. So obviously, when we take it all the way and apply it to the whole of GPT, etc., I think we are stretching beyond what they initially said. But then maybe people are applying it to that. I don't know.
No, I don't recall the 2D conversation. Asif, the I think what happens, at least on the transform world, is that there, in terms of curvature, right? There are certain areas which are highly curved in the optimization space,
Mhm.
and there's certain areas which are flat, and there's large areas which are flat where the optimizer is moving too slowly. Um, and when the gradient is very high, then you tend to take larger steps, which is again self-defeating. So what muon is trying to do is to just normalize all of that. It actually sets all the eigenvalues to 1, um, basically creating a orthonormal basis for the span of the loss function. And on the face of it, it seems like, okay, if you have certain large eigenvalues, you just set it to 1. Why would that help? But in the literature, they say that it does help because of these such landscapes in very large LLMs to just normalize the different eigenvalues.
So, Richard, so that part is there. I mean, muon was one of the first optimizers that carefully looked at the curvature
Right.
of the and the fast-moving and slow-moving or slow change directions.
Correct. Yeah.
It's gaining a lot of attention now. It's also a distinction between the preference of supervised fine-tuning and reinforcement. There is also, look back at the original muon paper, you'll see what I'm talking about. It has
I
to do
see.
with parameters. Yeah.
Okay. Yeah. On this one, I'm on this paper. I've struggled with it. I still don't know what the answer to the main title of the question paper is. Why do they not memorize? And how does it contrast maybe with the transformer-based models where recent research suggests that it memorizes and most of the memorization is actually in the feed-forward layers, FFN layer. So if they don't memorize, how do they produce new information out of it?
Richard, can I try to articulate it? Since you are familiar with information geometry, let me put it a bit more mathematically. See, what they are saying is, see, you have the score function, right?
Mm-hmm. Mm-hmm.
Now, the score is a force. In the very first paragraph, they say that it lives in the cotangent space, right? It is the gradient of the probability. So I mean, mathematically, it lives in the cotangent space. And what they're saying is, if you do a spectral decomposition of the vector of the flows there, the integrated vector flows, you will realize that they are big eigenvalues, the low modes or the modes that you generalize over. But when you bring lots of data, that landscape, that surface gets highly ragged. And because it's
Mm-hmm.
ragged, when you bring more data, it takes a very long time for the model to start figuring it out in some sense or fitting to it. And that's why the early modes get discovered quite fast, the slow moving, smoothing modes, and the less smoothing modes, or the raggedness of it. Think of it as almost like higher harmonics in the spectral decomposition. And the gap between them widens. That's why you have the metastable basin of in which you train the diffusion model, and you notice that very early on, very good pictures begin to emerge. And it also explains a counterintuitive thing. I think this paper is very, very insightful. That's why I like it very much, because it sort of explains why, uh, like the answer to the question is, why does it not memorize? The answer is not that it doesn't memorize. Answer is that it does memorize, but that gets progressively delayed far out. And I think I remember or recall a body of research showing that yes, diffusion models do degrade if you keep training them. With a transformer, that doesn't happen, right? In a transformer, what you would say is you go on transforming. I mean, you don't see much degradation; it flattens out. The loss curve flattens out. But with diffusion models, you have this unusual thing that they degrade after some time. And this paper,
Okay, so it's more a comment on the training dynamics of it being very different than just saying that it doesn't memorize. It does memorize, but
it
with these
does.
studies.
That's what it says. That it does memorize, but by the time you achieve the empirical optimal score, the gap is too wide, and you have a wide basin of stability. That's all it is saying.
If that's the case, I think Muon will actually work well here. I'd be intrigued to look more into that
Yeah, but
because in this highly, if the curvature in some areas is very high, in other areas it's more flat basin, like you're saying,
mhm.
that's exactly where Muon is helpful. I think so. It'll be
Like I would imagine. See, I haven't kept up with the Muon literature. The first paper was remarkable, and I loved it because it was the first one that carefully looked at the information geometry. But frankly, I have not kept up with it. But if you are some variant of it that generalizes to these things, I think your intuition is right. It should be very applicable.
Mhm. One more question, Asif and Sneha. So, just like in the GPT world, there are some small models like Nano GPT is one that people experiment with. Is there like a corresponding nano diffusion model that one can play with?
I'm not a big expert in diffusion models, so actually I wouldn't know.
Uh, okay.
Maybe Sneha can have a comment there, or
Right.
somebody else has a comment there.
There's a few I think there's like DIVO, or you mean more like industrial ones, like from like Google.
No, more like toy ones could be fine. I'm not looking for any industrial ones. More that they should be open weight, obviously. That I can um, mold to my data sets and basically it'll just like this conversation, right? Try different optimizers, plug and play, and then see how they behave at a
Mm.
small scale.
Small scale.
Well, when I may say small scale, I have a few GPUs. I don't like the GPUs like tens or hundreds of that level.
I think I think Stability AI has a few on Hugging Face, but I'm not sure what the size of those are. Um,
Yeah, those are more production level. Those are like the big ones.
yeah, those are production.
That's fine. One more question. So these in the models in this paper, were they mainly of the image generation type, or were they also the large language? I mean, language generating.
Mainly image. It was basically this whole thing was tested on an image data set for this paper. So,
Okay.
yeah. Oh,
You're probably aware there's research coming from I think Stefano Ermano's group at Stanford, which is doing the text diffusion models,
oh,
and
okay. Stefan.
it's they claim it's much faster, and the demos are really cool. So if there's a toy version of that, that'd be ideal to play with.
Oh, that's really cool. Like what exactly is this is this research on?
It's on diffusion models applied to text generation. So
Mm.
you give it a query, and then you see this, page populating with words which like they seem to be coming out of nowhere, and slowly it converges to a certain full answer of the query that you had asked it. So all the words are being generated in parallel. I wish I could probably find the link if I have a few minutes.
Yeah, I think it's also, yeah, I don't know too much about text related generation for diffusion. So it'd be good to learn more about that too.
Yeah, I'm not finding this thing again, but the company name appears. It's called Inception AI. They recently had a fundraise. It's the company by the same people, Stefano Ermon.
I think I think one recommendation maybe is like if you want to look into Comfy UI for looking at and exploring more small diffusion models. That's what's being recommended.
Comfy UI. Okay.
A lot of these models are being like played on. Yeah.
Sneha, thank you for volunteering to this excellent presentation. It's a very good choice of paper and really well explained.
Thank you. I think there's a lot more to really learn from this paper. So I recommend everybody to take a look into this as well. Even the mathematical proofs, because this is a 40-page paper.
Yes.